Hey everybody, it's Andrea. Before we start today's show, I have a super quick announcement to share with all of you. Beginning in April, I'm going to be launching a series of college to career live weekend boot camps to help graduating seniors as well as juniors who are confused about what jobs or careers they might want to pursue when they graduate. So imagine going from confused to confident with at least 3 different career options you'd be psyched to explore by the end of day 1 of the boot camp. And then learning the tools, tactics, and the strategies to find those jobs by the end of day 2. The boot camp is live and it's led by me over Zoom. And you can learn more about it at College to Career Academy. That's college, the number 2, career.academy. Or you can just look me up on LinkedIn and check out the featured section of my LinkedIn page. I can't imagine a better graduation gift for the college students in your life. Thanks so much for listening, and I know you're going to enjoy my next incredible guest. Hi there, I'm Andrea Koppel, and it's time for coffee. The podcast where you get to hear firsthand what the jobs and careers that interest you the most are really like. Hey there, Java junkies. Welcome back to another episode of T for C. If you're interested in learning more about what systems biology is all about and what it's like to be a researcher who spends a lot of time in the lab, then this is the episode for you, because my next guest is the chair of systems biology and a professor of systems biology at Harvard Medical School, where she's worked since 2004. But before I introduce you to Dr. Galit Lahav, I want to make sure you've signed up for the Java Junkies Journal. That's Time for Coffee's newsletter that features career advice and inspiration based on insights that I've gleaned firsthand from interviewing hundreds and hundreds of professionals in dozens of different industries. And I kind of promise you're not going to find them anywhere else. Just head over to the Time for Coffee website at time4coffee.org, and the words are all smushed together. And the sign-up box is right there. Now, my Java-loving, aspiring systems biology researchers, please grab your mug and take a chug of your favorite caffeinated brew, because it's time for another caffeinated career conversation. And my guest is Dr. Galit Lahav, the Novartis Professor of Systems Biology and the Chair of Systems Biology at Harvard Medical School. Dr. Lahav has been recognized around the world for her excellence in both teaching and research through awards and honors, including the Vilsack Prize for Creative Promise in Biomedical Science and an award for excellence in mentoring. That's actually one of the most prestigious awards at Harvard Medical School. And through workshops and science communications trainings, she's also created many opportunities for junior faculty and postdocs to cultivate their own leadership skills. Dr. Lahav is currently spearheading an initiative to make Harvard Medical School a destination of choice for women in science through the expansion of both recruitment and support for women faculty. And if you're interested in learning more about how to get into systems biology research, please check out the show notes for this episode to see if Dr. Lahav's Espresso Shots interview has already dropped. Dr. Lahav, Galit, welcome to Time for Coffee. Are you still caffeinated and ready to go?
Hi, yes, I am caffeinated and very much ready to go. Thank you so much for having me.
It is absolutely my pleasure. And I want you to know, as I was preparing for this interview, I started learning about the research that the air that you breathe every day, known as systems biology, which I believe became an approach not that long ago, in about the year 2000. And it uses the power of systems thinking, and we'll get into that, across traditional disciplinary boundaries. But would you be kind enough, Dr. Lahav, to elaborate a bit more, to kind of tease out how it works and why this field even exists?
Yes, of course. So you're right. This is a relatively new field in the beginning of early 2000. And actually, the department that I'm in was the first department in the world, the first systems biology department in the world. And now, of course, there are many, many more. And so the idea is that all systems across biology, they share a same, what we call design principles, whether it's the human body or a plant or a microbe. And so if we want to understand how things operate, why disease emerge, or how to treat disease, we need to look at the complex interactions of many signaling pathways and identify those principles, those mechanisms in a quantitative way. And so to do that, we have to merge biology and medicine with other disciplines such as engineering and physics and math and computer science, and use them to very accurately understand how our body operates and predict how it will operate under different conditions or disease or health conditions and or treatments.
Love it. Now, at your lab at Harvard Medical School, your systems biology lab, where you are the Novartis professor of systems biology and the chair of the department, you've been doing some absolutely fascinating research into why individual human cancer cells often show different responses to the same treatment. And that is so that you can actually identify new therapies to increase the likelihood that anti-cancer drugs will be more effective. Is that an accurate overview?
That's a very accurate overview. It's exactly right. What we do, we take cancer cells and we treat them with anti-cancer drugs or radiation. And many times we see that even though they're all identical, they behave differently. Like some of them will die in response to the treatment, and some will survive, or some will stop grow for a certain amount of time and then continue to grow. So we're very interested in kind of going into the decision making of each individual cell and understand why it varies so much and how we can control it.
And it involved you actually pioneering new approaches for quantifying the behavior of what's known as P53, which is a protein in single living cells. Can you elaborate on why P53, why this protein is so important?
Yes. So P53, it's called the guardian of the genome, right? It's one of the most important genes that makes sure that cancer does not develop. And in many types of cancer, P53 itself is mutated. And the reason is that when our cells acquire mutations or damage to their DNA, P53 levels go up, and then it makes a decision whether the damage can be repaired and this cell can survive, or the damage is just too much for the cell and that cell will die, which eventually will save the entire organism because getting rid of harmful bad cells, right? And so when P53 is not doing its function, those bad cells can proliferate and develop into tumors. And so you're absolutely right. One of the main approach that we pioneered is to fuse a fluorescent protein, a protein that shines that we took from jellyfish to P53. And now we have a little flag, a little light, fluorescent flag in each cell that we can see what P53 is doing in each cell in response to the treatment, and connect that with the final outcome of the cells, and then we can control it and change it, and it's beautiful and a lot of fun.
Oh my gosh, you took a cell from a jellyfish as a way to have like a little flashlight on each?
Yeah, it's a gene called green fluorescent protein. It has been widely used in microbes, and we were the first ones around in early 2000 to fuse it to a human gene and create videos in real time of how P53 fused to this fluorescent gene behaves in human cells.
So most studies prior to your work were kind of looking at many cells together.
Right.
But what you did, the pioneering work you did, was to focus on a single P53. How is that different from other research that happens in laboratories like at NIH and others that may not necessarily be systems oriented?
You're absolutely right. Prior to our work, everyone that looked at P53, they just took hundreds or thousands of millions of cells together and then averaged their collective behavior. Now, the problem with that is that imagine that 99% of the cells behave in a certain way, but then 1% of cells do something a little crazy, right? When you average the collective behavior, there's no way you can identify these weird, crazy outlier cells. And when you study cancer, that's really important because cancer emerges from sometimes one crazy cell. And also sometimes you have group of cells that behave differently. Like I can tell you in our case, we discovered that P53 oscillates in cells, but the oscillations are not synchronous between cells. So when you look at the collective average behavior, it's very easy to miss them, but only when you look at individual cells, you can see them. And so I think in the last 20 years, it has become really important to look at individual cells and across many, many fields of biology and medicine. So now there's quite a lot of research, beyond P53 on many other pathways in biology, developing tools to look at how individual cells behave.
So how does taking a systems approach to looking at a single P53 cell work?
So when we collect these movies of P53 from hundreds and thousands of cells, we get trajectories of their dynamics over time. And these are messy and complicated. And then we need to bring tools from math in order to create mathematical modeling and complicated statistical analysis to extract features and principles from these dynamics. Like I mentioned, the oscillations, we are working toward understanding what's critical in these dynamics. Do cells read the frequency of the oscillation? Do they read the amplitude? Do they read the integrative level? And to understand how information flows from proteins that regulate P53 and downstream to what P53 regulates. And so collectively understanding the system through capturing thousands of different dynamical behavior of P53.
So what are you doing right now in the lab? And actually, are you even in the lab in the middle of the coronavirus? We're doing this interview at the end of January 2021. Are your fellow colleagues able to even be there in the laboratory?
Yeah, great question. So I now have a research lab of about 12 people, including students and postdocs. Most of them are doing experimental work. So yes, they are going to the lab to do the work because they need to be able to have access to materials and instruments. Some of them are doing more theoretical computational work. So they work from home. I have not been in the lab for, a very long time. All the work I do from home. So a big part of my work is to mentor the people in my lab, to help design experiment, to go through data, to decide about the next experiment. So we do all of this virtually right now. So they do the bench work and then we meet and brainstorm and do all the thinking through screens, which is way less fun.
Definitely. So I have the benefit of having had an opportunity to look through your super impressive resume and highlights of some of the research that, in fact, you're working on right now. And one of the things that I noticed, Galit, is that you have different research that goes on for years. So I was looking here and you have something that began in September of 2016. It just ended. Oh no, it's ending in August of 2021 with a major goal to provide quantitative understanding of the pathways controlling growth and senescence. Is it senescence? In normal and cancer cells, and to develop novel strategies to selectively push cancer cells towards permanent arrest. So stopping them in their tracks.
Right. Yes.
And how often is it that you succeed in that period of time? And how often is it that you need to continue? You need to get additional funding to continue that research?
Yes. So what you're referring to, these are grants that we have written, and these are the resources that allow us to run our research because research is expensive. And these grants will be put usually for 4 or 5 years, and we develop a research program, what we are planning to study. And you're absolutely right. Many times while we study, the question change, or we realize, there's actually something a little more important and interesting, and we get sidetracked and we focus on that. The truth is that everything we discover open new questions. We never reach a point that we say, all right, it's done. We understand it all. We can go home now.
Like it's all done.
It's all done. Exactly. And that's what actually I love about it, right? Because first of all, the open question that our research provide, it's not that we are the only ones that are going to follow up on that. Many times other people in other labs in other countries pick them up. And many times I get emails from people saying, I read a paper from your lab and it made me think about that. And then I did this experiment. And so you have a very big impact on the open questions in the field and what people do with them afterwards.
Gotcha. So what does a typical day look like for you, Galit? In other words, now you're not in the lab, but before the coronavirus, how frequently would you be in the lab? And when you're not in the lab, what are you doing?
Okay, so there are a few kinds of a typical day. Okay, so one kind is a day that I go to the office. I have an office that is right next to the lab, and I get there around 8:39 after dropping the kids at school, and I have what I call, back-to-back meetings. So meetings, and these meetings can be meeting with people in my lab to discuss their research, to go over new data, to think about how the next experiment, to analyze the data, to just brainstorm new ideas or how to solve problems. These can be meetings with faculty in the department. Since I'm a department chair, I'm also responsible for them to talk about any issues that they have, to help with their development, to discuss how to enable their research. It can be, if it's a day that I'm teaching, it can be working with students in the classroom, and it can be 2 or 3 hours of teaching. It can be meetings with the Harvard Medical School leadership to work on policies and guidance. And it can be meetings with administrators to work on budgets, on space issues, on facilities, and so on. So it's meetings. And I would say probably about 3 days out of 5 are like that. Now, I've learned I have at least one day that is no meeting day, like no one can get on my calendar. And it's actually the only day I can think. And I use this day many times, first of all, to catch up on stuff that I need to do, emails and writing, but most importantly, to work on papers that I'm writing, to write grants that we talked that we need money for to do the research, to read papers, to be a scientist, right? So it's during these meetings, I really don't have a quiet moment to think. And to be a scientist, you can't just do it in half an hour between meetings. You really need long chunk of time to think. So at least once a week, I have a no meeting day that I practice and remind myself how much I love being a scientist. And I've also started to incorporate something that I call incubation days, which I love. And I think they're really critical. And these are spontaneous days that, again, have nothing on the calendar, no meetings, but also no task like work on this paper and revise this review. And it's almost like whatever happens, happens. And it's me spontaneously, if I'm in the office, going and chit-chatting with people, suddenly finding a whiteboard and starting brainstorming a new idea, browsing different things online, even just taking a long walk. Like, I actually think that we all work way too hard, and it's just, creativity is so important for scientists. And I think taking these breaks and allowing time to breathe and think is just so important. It also helps to bring joy, I think, to the work that sometimes we forget about.
So I'm actually reading this book. Dr. Lahav can see this. It's called Rest: Why You Get More Done When You Work Less. It's by Alex Sujung Kim Pang. I highly, highly recommend it. To your point, we actually are more productive. It's counterintuitive. We're more productive when we give our brains rest, real rest, on a regular basis, not just like the way we do here in the United States, where it's like, okay, I have my 1 week vacation a couple times a year, but on a daily basis to take those breaks.
Yes. And I want to say one more thing about that, because it's something I'm very passionate about. I think there is a risk. There is this notion in science, probably in academia and beyond, that in order to be successful and, the best of the best, you should want to think and do science all the time. And I remember when I was a student, I was really worried about that because I wanted to have a balanced life, wanted to have hobbies and wanted to have kids. And I thought, okay, if I'm someone who doesn't want to think about science all the time, maybe it's not the right profession for me. And I've learned throughout the years, there are many ways of doing this. And you can have plenty of hobbies and friends and kids and decide this is the time I'm focusing on science and this is the time I'm detaching myself. And this is okay. And you can be very successful even with this lifestyle.
Excellent. Such an important point. And I know, as I said in the introduction, you've been leading an initiative at Harvard Medical School to make it a destination of choice for women scientists. And you've done that through recruitment and support for women faculty. Why is something like that so needed? And I'm guessing maybe not just at Harvard Medical School. How common is it now to have women in the lab? What is the male-female breakdown like right now in this field?
Yeah, so it's interesting because you see in the undergrad level or even graduate level, you see equal representation of female and male, which is great. But then when you start to go higher at the postdoc and especially at the faculty professor level, the percentage of female drops significantly. Now, in my field, systems biology, it's a more quantitative theoretical field, we are in about 20% female faculty, which is extremely low. And so we really need to ask ourselves why and what we can do to change that. In my mind, more role models is one of the solutions for more young females to see that women can succeed and again, can live quite a balanced life while they are working in this demanding job.
Fantastic. So I would like to flash back very quickly to when you were an undergrad. You went to Technion, which is Israel's very prestigious Institute of Technology, and you graduated with a BS in biology. Did you know what you were going to do with that degree when you graduated?
Not at all. No. I know that some people start college and they're just like, know exactly where they're going. I honestly never, ever knew. I sometimes laugh that I'm still not sure what I want to do when I grow up. And I'm serious. Like, it's not a joke. I feel like I went to study biology because I was fascinated about biology and medicine. I actually also really love math and physics. And at that time, there was no field like systems biology. So I had to make a choice. I couldn't study all of it. So I went to the Technion, which is an Institute of Technology. And the good thing for me was that in the Technion, they offered a lot of courses in the other field, the other quantitative field that I could take as a biology major. So I was able to acquire all these skills, even though the degree was in biology. But again, it wasn't there was no intention of what to do next. And kind of one thing led to the other.
And how did one thing lead to another?
Yes. So at the end of my bachelor degree, one of the professors reached out to me and said that she really enjoyed my participation in class and teaching me, and if I want to come and do like an internship in her lab. And I was so flattered. I'm like, oh my God, she chose me. Of course, I can't say no. And I worked in her lab and I really loved it. I discovered the fun of doing research and just decided to stay in the lab. She offered me to stay in the lab for my graduate work and for my PhD. And so I stayed there and completed a PhD in research. And to be honest, at the end of my PhD, I was kind of exhausted and confused. I was like, I don't know what I want to do next. I just don't know if research is for me, if I should stay in academia, should I go to industry? So I decided to take some time off. And I grew up in Israel, and it's very common in Israel to travel. Most kids travel right after the military, but I did my big trip after grad school, and I took a few months off just to travel and think about the next step. And at the end of about 4 or 5 months, when I was just out of money, I had to come back home. And it was interesting because suddenly I was hungry for research again. I felt like, I actually really want to go back and do research. My appetite for science and research came back. And it was also very clear to me what needs to be in my research in order for me to be satisfied. I realized it must have to do something with human disease. Like I need to feel like I'm making an impact. Must be quantitative. Like I have to work with numbers, and it must involve microscopy because I just love imaging cells. And so I found a lab at the Weizmann Institute. This was a lab of Uri Alon, who's a physicist who moved into biology, and joined him for my postdoc. And basically in his lab, I started the research that I have continued to do in my lab for the many, many years.
I love that. Thank you so much for sharing. I try to ask all time for coffee guests this next question in particular, and that is to share a time in their professional lives when they failed. I know you very much believe in the importance of being persistent despite failures and in resilience. For other guests who are not in a laboratory, maybe they got fired or they quit or whatever it was, but it was a painful experience. And the most important thing is how they persevered, how they got through it, and if there was a lesson they learned in the process. Could you share an experience that you've had, Galit?
Of course. So first I would say I failed so many times. I've had so many papers rejected, so many grants rejected. But the one story I want to share is actually from my postdoc time. As I said, I was a postdoc at the Weizmann Institute, and I developed this new method to look at P53 in individual cells. And we had to run videos under the microscope for many, many hours. And at that time, we did not have the equipment to do it. And so my mentor suggested that to send me to the Rockefeller Institute in New York to collaborate with another lab there that has that instrument. And so we did that, flew me to New York, and I went there for about 2 months with a very specific goal of acquiring movies, videos under the microscope of these cancer cells responding to drugs. And it was a very expensive, fly me to New York and housing in New York. But we felt like it's really critical for my research. And the trip was a disaster. Like nothing worked. Nothing. The cells in Manhattan behaved completely different than they were in Israel. And the microscope crashed and the computers crashed. And like every day I came to the lab, I tried the experiment again, and every day something happened. And it was a few days before I was supposed to go back to Israel, and I was able to acquire nothing. I felt horrible, like so ashamed and guilty that I spent all this time and money and wasn't able to get any data. And so I remember my postdoc mentor, Uri Long, called me in the lab and asked me how things are going. And I told him it's a disaster. It's terrible. I have nothing. But I was like, don't worry. Like I have, 4 more days and I'm going to work days and nights until I get this data. Like I promise you, I'll get it. And then he asked me, he said, Galit, have you been to any musicals since you came to Manhattan? And I said, oh my God, no, I've been to the lab all the time. And he said, what about museums? Did you go see any art and shopping? And I kept saying, no, I didn't do anything, really. I just worked all the time. And then he told me, this is what I want you to do right now. I want you to go to the microscope, get your cells out of there, throw them into the trash, and go and explore Manhattan. He's like, done. And you'll come home and we'll figure it out. And I was shocked. And I have to say, I did not follow his advice immediately. I gave it one more try, which failed again. And then the last 2 or 3 days, I was able to enjoy Manhattan. But, it had a really, really important lesson for me, which I cherish. Behind running experiment and being productive, there's a human being. And you really need to care for that human being beyond data acquired or productivity. And so, again, this is something I implement in everything that I do with my students and postdocs now.
What a beautiful example, and such an important one that your mentor probably recognized. Whatever it was about those cells, you could have tried another 1,000 times and it wasn't going to work. Right. And yet here you were in a brand new city and you weren't experiencing life. You were missing it.
Right.
Oh my gosh.
And guess what? Yeah. I came back and we figured it out, right? We managed to figure it out, and I came back way more happier after having fun in New York for a few days.
Fantastic. What an amazing story. Final question. If you could go back to college, back to Technion, and do it all over again, but based on the wisdom you have right now, what advice would you give yourself?
I think I would give myself permission to be a little bit more out of consensus. I was really following the rules, and I feel like sometimes we shouldn't try to fit so much and do what we are told. Like, for example, during my graduate studies or in college, the recommendation I got is to focus more on biology courses or working in the lab rather than take courses in physics and computer science because it was a waste of time. This is what my mentors thought at that time, right? Again, systems biology didn't exist. No one appreciated that. And I kind of listened to them, right? I did a little bit on the side, but not enough. Like, I wish I would just like break those boundaries and said, no, this is how I want to manage my degree. This is what I want to study. These are the skills I want to acquire. And I don't care this is the path most people have taken before me. I want to create my own. And so I got better in this, I think now, but I wish I had the guts and the courage to do it back then.
Well, hopefully our young listeners will be inspired by your call to action, that they are and should be the ones who are leading their own academic discovery. And after they graduate, their own professional journey.
Yes.
They need to block out the noise from all of the adults in their lives and tune into who they are.
Exactly.
And what they want. Listen to their gut, which is actually listening to their brain, which is, I know, something you appreciate because the gut is the second brain. Galit, I want to thank you so much for the work that you are doing and your colleagues are doing that is so vitally important for so many people who either have cancer now or may very well get cancer, and your dedication and commitment to helping them live a fuller life, and also for making time for coffee today with me and the Time for Coffee community. This was just wonderful.
This was a pleasure to be here. Thank you so much for the opportunity. I really, really enjoyed it.
Thanks so much for listening to Time for Coffee, where the professionals in the jobs that most interest you always have time to grab coffee 24/7, no matter where you live. I have one quick favor to ask you. Remember to rate, review, and subscribe to Time for Coffee. Thanks so much.